for a polytropic process. We have 0.15 meter cube of an ideal gas at a pressure of 15 bar and 550 Kelvin, capital K for Kelvin, is expanded isothermally to 4 times the initial volume. It is then cooled to 290 Kelvin at a constant volume, and then compressed back polytropically to its initial state. Calculate the net work done and heat transferred during the cycle. As usual, pause the video, note the parameters, then let's go to the solution. So, as with every engineering problem, we start with the given. We were given volume V1 of 0.15 meter cubed, P1 of 15 bar, T1 equal T2 equal 550 Kelvin, V2 over V1 was equal, that's V2 was 4 times V1, T3 was 290 Kelvin. So now, having written the given, we'll try to draw the circle. The circle says an ideal gas at a pressure was expanded isothermally, state 1, state 2, and then cooled at constant volume and compressed back polytropically to state 1. So this is the PV, pressure volume diagram. And we know that for an isothermal process, PV is equal to a constant C. For a constant volume process, C is equal to constant. And then for a polytropic, PVN is equal to a constant. Furthermore, we can write for the isothermal process, that's process 1 to 2, that P1V1 equal P2V2. So that means P2 is equal to P1V1 over V2. If I put the values here, we would have P1 over 4, and that would be 15 over 4, and that is 3.75 bar. Next, I can also calculate the work done in this process. Work done, W12, we've seen this before, is equal to P1V1 ln of V2 over V1. So if I write, I would have P, which is P1 V1, which is 15 P1, 15 bar times 10 to the power 5, V1, this, if I multiply these two, I'll have this here as 15 times 10 to the power 5 times 0.15 times the log of V2 over V1 is 4. That's times the natural log of 4. So everything becomes 311.9 kilojoules. That's for the work done from process 1 to 2. The next we want to consider is 2 to 3. Is there any work done here? Remember that for the process 2 to 3, the work done is 0. Work done 2 to 3 is equal to 0 because it's a constant volume process. Constant volume process that has no movement in boundary, movement in the system boundary. Okay, so we now move to process 3 to 1. Now, for process, and this process 3 to 1 is called a polytropic process. So we would write is P3 V3 N is equal to P1 V1 N. Okay, which we can write that P3 over P1 is equal to V1 over V3 to the power N. We can also write okay, that's correct. We can also write that the ln of P1 over P3 is equal to N, the ln of, because I'm taking ln of both sides, is equal to the ln of V3 over V1 times N. N times ln of V3 over V1. So, we are therefore going to write for N. We can get N by taking this one to be the denominator here. So making N subject of the formula, we would have N is equal to N ln 15 over 1.98 over ln 4, and that's equal to 1.46. Then we can therefore write the work done, because work done for a polytropic process was 3.1 is equal to P3V3 minus P1V1 all over N minus 1. Putting everything inside here, we have 1.98 times 10 to the power 5 times 0.6 minus 15 times 10 to the power 5 times 0.15, okay, divided by 1.46 minus 1. So this will turn out to give us a value of W as, so our W31 from state 1, from state 3 to state 1 gives us minus 230.87 kilojoules. Remember, we have automatically converted from joules to kilojoules by dividing by 1000. So we can now calculate what the net work done in the system is. W net is equal to W12 plus W23 plus W321. W12 was 311.9 plus 0 plus minus 230.87, which is 81.03 kilojoules. So since we've written that, we call that from first law, integral of the Q is equal to second integral of the Q is equal to second integral of the W. So that means that I can say, therefore, that the heat supplied Q is also equal to 81.03 kilojoules. Okay, so this is the heat transferred during the cycle. Heat transferred, of course. This is cyclic integral for the whole cycle. So heat transferred during the cycle. Okay. This is kilojoules, small k,